Hello everyone, this is Ron Baden with Untitled Functional Programming, and I welcome you to another episode of the Haskell Study Group. Before we get started with today's topic, a couple of announcements. Next week, unfortunately, we're going to have a brief hiatus, and Haskell Study Group is canceled. So those of you who are going to tune in weekly to our stream, apologies. Something came up, and I couldn't host it next week. Additionally, as usual, AFP is looking for people, looking for speakers, folks who want to talk about functional programming in your language of choice, whether it be Haskell, Lisp, that's all the Lisp dialects, Common Lisp Scheme, Clojure, Dylan, and so forth, or one of the mainstream languages such as C++, C#, F#, and so forth. If you have any topic ideas, please let me and Judd Taylor know. I am Bugram on the Functional Programming Slack channel, as well as on Tech 404 if there are folks here that are part of the Tech 404 Slack workspace. You can reach me in both places and come up with ideas, and we'll add it to the schedule. So without further ado, let's start talking about today's topic. Last time, I briefly mentioned that we're going to be discussing functions again today and functional patterns. Functions is an integral part of writing Haskell, and may come as a surprise that since Haskell is a functional programming language, or functional programming for the and introduces a lot of functional programming patterns. Might come as a surprise that you could go really far with just writing normal functions inside of Haskell, and we've been up until now already discussing a lot of that. If you recall, a couple of weeks ago when we talked about and introduced the basics of Haskell inside the REPL, we introduced things like currying and uncurrying, and how to deal with multiple parameter functions, what a function is in terms of the Haskell mindset, and so forth. We're going to briefly review some of that information today, as well as talk about things like high-order functions, pattern matching, guards, as well as introduce you all to and have a much more deeper discussion on point-free or task programming, a style that a lot of Haskellers tend to encourage, if not actively program Haskell software in. This pattern does take some getting used to, in the sense that you are going to be dealing with a particular type of programming that involves a lot of partial function application. But once you see some examples on how we leverage it, and we've kind of already done some of that when we were talking about function composition, it'll become clearer to you in terms of why this programming style is kind of preferred. So we already kind of know that in Haskell, when we talk about functions, what a function really is. It is basically a mathematical mapping between a particular set of values known as your domain, okay? And this is your input value, all right? And a set of output values known as your range, right? Haskell specifically supports this mathematical definition in the sense that all Haskell functions take a single input, if you recall, and return a single output. It could be of any type, okay? And we've already seen some examples of this. So we've written an example like this, where we take a value x and we add 1 to it, okay? When we actually look at this in the REPL, you would probably understand that this parameter, okay, is of a particular type, okay? We've already seen this also with functions such as a simple static function. Although this certainly does look like a value, this is actually a value with no parameters, is what it really is. Okay, so it's a function with no parameters, and we could see this when we go and let's say that we, apply it to some, my value equals my number, all right. And we don't specify the type here. If we go in and look at the type of my value, you'll see that my value has already been inferred as an integer. Although, and again, this is something we've discussed before in previous episodes, my value, technically, when you are writing this inside your editor, you'd want to actually specify what type it is. It could certainly infer at load time. This information will just throw this warning that there's a missing signature for a top level binding. Okay, because we're loading these values at load time. Okay. If we actually look at the add1 example and we do a type of add1, we'll also see that that it just takes in the integer signature, the type signature that we provided for the function that we've declared inside the load file. It just doesn't go from just from here, right? Let's say that we continue with this this mynum value, and we instead provide now, instead of another value that takes in a call to my number, which allows the inferencing to happen. Let's say that we go in and we just say that mynum now has a parameter, all right? If we actually look at the type signature of my value, you'll see that it will take in any sort of type variable t, p, and we will return some sort of integer because that is actually the return value of my number. In this sense, my value has no longer become a function that takes no parameters, but it's become a parameterized function. Specifically, the p is a type variable that is now polymorphic. And since we didn't specify any sort of class constraints on top of the type variable, refer to our type class series and resources that you're reading on type classes. This is going to be the maximal polymorphic type that that Haskell provides in terms of supporting. Now, if we go and say, for example, and let's go ahead and do it here, f equals f plus my num, and we load this, and we look at the type signature, you'll see, oops, sorry. You'll see that when you use my value, that the Inference Engine actually kicks in because it recognizes, and this again goes back to how functions are applied. it recognizes that my_num returns an integer. And f returns a type variable. Okay. Remember that operators tend to be left associative, but since addition is has a numeric type class constraint. Well, it actually has a type variable that has no constraint, and it has a value that has a constraint of integer. It's going to take precedence the more specific value than the generic value. And this is why, although operator plus is left associative, this type signature ends up giving us that we need two integers in order for this function to actually occur correctly. All right. The main thing to note here, and the main thing to realize is the type inferencer does quite a bit of work for us to handle a lot of the basics of inferencing when values are concerned, when parameters are passed into a function. It does its best to make sure that all constraints are properly satisfied, starting with the most specific and then working its way up to the most generic. Okay, so there's a question. So my_num is basically the constant combinator, or the k combinator. I would have to go and look that up again. I don't know, but I think you might be right. I'm pretty sure that that sounds correct. That it is the k combinator. But again, I have to go and I always have to keep the flock of the mockingbird like diagram that I found. And I'll post this this kind of reference that I use in the YouTube comments. Let me see here. This is the one with all the type signatures. Yes, you are right. I just went into the Wikipedia page for the SKI combinator calculus, which provides some of the combinators already available to you. The K combinator is just a constant. Let's get back to this. We also kind of went through this, so this is going to be another brief review, but we've seen also how we might be able to leverage class constraints on top of signatures as well. So for example, instead of adding this, we could certainly, instead of adding this, we could have certainly done something like this as well, where A is taking A, and now we're now polymorphic. We're no longer just taking integers, but we're polymorphic only in the sense that we're any numeric type is actually a valid input to this add one function. And if we load this and we accidentally say pass in a string, it's going to go in and blow up. It's going to go and give you this type error saying that it can't create a data constructed value of a number, of a numeric, out of the string itself that you provided. So the other thing to kind of note is if we actually pass in two values into this, my value fg equals f plus my num, okay? And we, instead of 1, and we check the type signature of this, you're going to see that this is going to generate a function. Actually, let's go ahead and do this a little bit more specific to illustrate this point. If we go in and look at the value, you'll see that we end up getting two type variables here. And if you recall, in Haskell, these type variables don't necessarily have to be the same type. They could be different types, but they could also be the same type. These generic variables do not get bound to until we are dealing with parsing and substitution of the values into the function. At that point, we'll check the types of that and then verify that those types match the constraints. In this case, that they're of any two types, and it will return an integer. Although you saw already if we add this integer, the appropriate pieces of the puzzle gets inferred by the Haskell compiler and REPL, and you'll end up populating the appropriate parts of the type signature accordingly. All right. Does that make sense for folks? Just checking here. Okay, cool. We've also seen, as you saw here, that Haskell allows you to pass in multiple parameter functions, have multiple parameter functions, but a multiple parameter function inside Haskell really means a series. It ends up being a curried function in that all the function arguments must be applied before the actual result is evaluated. And you could think of this as a series of functions, each of which taking one input and returning an output that contains the remainder of the parameters of the function unbound. Excuse me. If we take an example that a little bit more specific, that takes in 3 parameters, each of which are unbound in terms of their types, so there's no type constraints on it. And we take in these 3 values and concatenate them, and we look at the signature of this. One thing to note is, although the function itself defines this as concatenation and stuff, but it still represents the fact that these aren't heterogeneous. All 3 are inferred as being of the same type, the generic type variable A. All right, and if we obviously populate any of these with the one specific thing, you'll see you'll end up getting this type error where it's trying to match the generic type value with the integer that list that you said that you'd want to connect to. This kind of shows you. Okay, so there was a question. I don't understand your question. Could you be more specific as to the question? The question just says why. Why? Okay. Uh, Comment was is I meant yes. Okay. I did not. Uh, I misunderstood what you were asking, and I didn't realize that that was a comment. Okay. Thank you. Um, okay. So the bottom line is this example that I'm just showing you here, that I'm trying to illustrate, is the fact that you can't just willy-nilly specify uh, specific types within the type signature, expecting that Haskell will at some point realize that that is the underlying type that you would want. If you're going to be writing a generic function like this, you would want to uh, just maintain the type variables and then specify a type class like this, and you'll end up getting the same idea. Or make all of these three input types integers, because Haskell won't necessarily take your signature and, as you can see here, take that integer and then reapply the actual inferencing of the signature accordingly. And this is regardless of area that you put this function in. All right, you go and look at this now. It looks like this actually worked. Hold on. Oop. Okay, hold on. Let's clear this up here. Okay. Yeah, so this is regardless of the area that you're putting it in. You'll end up getting the same issue with the compilation not recognizing these generic type variables, and it will specifically tell you that you're trying to take a rigid type variable for, bound by a signature, saying that for all A, the integers should be able to concatenate with these type variables, and that's not enough information for the Haskell inferencing engine to determine the correctness of the type signature, and it will just go ahead and say, sorry, I do not have any information on that. And obviously, this, regardless of types, you're going to end up getting the same issue. Okay. If we just clear this up and do this, you'll see that now you'll get the same problem, right? This type issues of variables. So bottom line, if you're going to be doing something like this, just if you're going to write a generic function like this that does concatenation or some complex logic, just go ahead and add your type class constraints at the top, and this should all be good. All right. And again, here in this multi-parameter function that we saw, these guys are just two type variables that are allowed but not required to be different types. Okay, so these are both polymorphic types that don't necessarily need to be the same. Okay. When you're applying a function, as we've been talking about so far, when you're talking about binding parameters, okay, you are talking about actually binding parameters not to um, uh, some sort of like memory location, what have you. You are actually binding the parameter to a specific value, okay, a specific concrete instance of some piece of data, okay, some data. And this is across the board. So if you're talking about at the type level, at the type inferencing level, type parameters, which is what these are, these type variables, these lowercase a's, these are, think of these as parameters, okay, these are type parameters, okay. These guys are bound to a type when the inferencer determines from a value the type of that value, okay. So when function application happens, you are actually looking at the value, figuring out its type, then looking up the function, determining if there are generic type variables, then taking that type that you just inferred, putting it into the function signature, making sure that the type class constraints are all satisfied, and then you're going to bind that value to a particular parameter in the function signature. So all that kind of works. Otherwise, you're going to end up throwing some sort of type error. I know that that's a lot to swallow, but that's kind of in a nutshell what Haskell is doing all behind the scenes. Okay, so during your development, you may not see all this machinery at work, but that's ultimately what happens when you evaluate a particular function to with particular values as its parameters. All right. When you're talking about value variable binding, okay, you are concerning yourself not only with function arguments itself, but you'll also be concerning with let expressions and where clauses. Okay, that is something to be very important. That's something to be aware of, and this is and this obviously gets into some issues when we talk about shadowing. All right, because you want to know where a specific function binds a value within the context of that function. Right. We don't know, as I said before, the result of any particular function until all values are bound to some sort of variable in a function signature. If we actually look at this example right here, okay, let's change this to being integer to integer just for the sake of the example, okay. Actually, let me just do this since I already have the signature here earlier. Let's see if I could just go and comment this guy. Command. Nope. Nope. Hold on. Not that. There we go. That's what I want to see. Okay. So let's uncomment this guy. And now we're all good. Okay. So we know when we look at this function and this signature that's taking an integer and stuff, when we're applying a value to x, we're going to check to first see that x is we're going to first check that the value passed in has x, is of type integer. And if it is, then we can say that x is now bound to that value. All of add1's variables are now bound, so now we can actually go ahead and complete this function evaluation, which again is just an exercise in beta substitution if you're doing this by hand for folks who are trying to do the lambda calculus by hand. But behind the scenes is essentially the same thing. We end up evaluating all instances of x to the value that was provided as a parameter, and the function is completely evaluated, and we'll get a result. All right. Again, you want to first type check, then the values are bound to the variables. In this case, they're bound to the parameters inside the function. and then we can actually go and get the result of the function. Okay, so if we add 1 here, you know that add 1 is just going to check that, see if 1 is an integer. Obviously 1 is an integer, so then it binds 1 to the value of, has the value of x, and it substitutes all instances of x in the body of the expression with 1, and we'll get 2 as our answer. And obviously, if we change this, it'll work the same way. Okay. If we end up creating a much more complex function, but we still have not yet, created so if we're creating a complex function with a let, but we're not and this example is going to ignore it's going to ignore, for the time being, it's going to ignore shadowing. We can see something interesting here. Okay, let's take, for example, let's say print pair of 5. Okay, so hold on. So generate and print pair of 5. This is a really contrived function that takes in an integer, and it's going to just generate a function that takes in an x. We're going to have an expression that has 5 in it, and all we're going to do is this is going to actually, the name isn't really clear. Let's just say print pair, constant pair is what I'll call it. All right, and let's say that in this example, that what we're going to do is all we're going to do is we're going to take in a pair, and obviously we can do this in other ways. All right, but for the sake of example, we're just going to go ahead and do something like this. We have our x, and we have our y, and we do this. Okay. And all this is doing is obviously treating it as a pair. Okay. Now, if we look at the print constant pair function, it's going to still maintain our integers as strings. I'm getting an error here. This next warning. Okay, so let me do this for the sake of making this more explicit. That warning you don't need to worry about. Like if we had this isn't going to cause any issues. We'll still be able to pass in, say, print constant pair with 5, and we'll get 5, 5. But the point of adding this is adding the type, since it's having some issues. It's basically warning that you might get into a situation of undefined behavior, although in this case it shouldn't. And that's why I'm just adding the type to y in this case. The point that I was trying to make, though, is that in the let expression and in the x is bound to first a 5 after it gets checked as being an integer. Then y, since we've already explicitly said that y is 5, okay, it gets type checked at the time that it's getting registered. And you saw that when we loaded the file, we get this warning. Since we've explicitly, in this particular example, specified the type, okay, we said that it's integer, it's not going to actually type check it. It's just going to assume that the y is some sort of integer, and all it's going to do is make sure that it's going to validate the value that you provided here. So, like if you said that this was a string accidentally, and then said treat this as an integer, you're going to get something different than what you would expect. Okay, and I'm going to show this here. You're going to end up getting an integer saying that, an error saying that you were expecting of type integer, but you casted the string has of type integer instead of, and it can't construct it from that string. So that's the main thing. And this language import overloaded strings gives you some additional things that right now we won't look into. But this shows you that the Haskell REPL will give you suggestions on how to potentially resolve some of these type issues that it's encountering. Okay, so let's change this back. We've got our load, and we'll see that obviously. Sorry. That all our integers signatures all match, and everything is kind of kosher again. Okay. Where this falls apart is ordering of the expressions inside of a let expression, because a let expression, as I mentioned before, is creating a lexical scope that all variables that are defined in the let expression are available only within that scope. All right. So if you have nested scopes, the parent scope is available in the child scope and so forth, but the innermost scope is what you're going to be dealing with. And where that potentially might be a problem is if you're trying to add, let's say we're trying to add, 5 and 7 to some function, okay? 5 and 7 to some input, okay? We pass in x. And we decide that, that z is going to be 5 plus 7, and then we do that y equals 5 in x plus z, all right? Because it's kind of expecting that z would already have what we want, okay? If we try compiling this, okay, you're going to see immediately an error, variable not in scope. Well, that makes sense because the fact that this is the outer scope, this is the inner scope. The inner scope defines y, the outer scope doesn't, all right? Make sure that you are actually putting the variable declarations in the right scope. Otherwise, you'll end up getting these issues. And again, this should all be very quick review on stuff that we've already encountered. And now we could do add 5 and 7 to say 5, and then that's going to be 22. Oh, sorry, it's going to be 17. We could also talk about, let's say add 1 x equals, so in actually say add 2 x equals let x equals 3 and x plus 3. And you can see what we're doing here is we're actually defining a function with the same variable, and the variable x is actually shadowed by the lexically scoped variable x, and this is going to end up, regardless of what you pass in, to this function, all right? Because although this function is misnamed, it still illustrates the point. It will always return 3 plus 3, which is 6. This is because, again, this goes back to the notion of what the let expression is. It is a lexical scope that holds all the variables that it has in it, and it takes precedence to all previously defined scopes, including the function level scope of the variables that are defined in the function level scope, although they may take the same name, all right? It doesn't actually do what some languages do, which is unless you define something as special, it doesn't try and take precedence of that variable's values over the current scope's values. This is a very consistent way of scoping variables and values, and it's actually commonly used in most modern programming languages. So I encourage you to actually go and look into the scoping rules in terms of it. We've already done quite a bit with let statements, so I'm going to just briefly mention that you don't necessarily need lets to actually go and handle this. Apparently, the REPL also has some ways of doing shadowing too as well. So, for example, if you have, say, x equals 5, y equals x plus 5, which means we already know that y is 10, so x is y, y is 10, okay? If you obviously use this in any normal expressions, it will just take the value at the top level, all right? But let's say that you define a z that takes a y and then do y times 10. Y is still 10 here, but if you pass in 9 into z, y locally scoped within the context of the function variable z, you are going to end up getting 90 instead of what you might have thought you'd get, which is 100. And that's because in that scope, in that variable scope for z, y's innermost scope is defined as being whatever is passed in by the function. Okay, so this allows you to do things like this, where you're taking the top level variable y, pass it into the function z, and then you end up returning the appropriate thing that one might expect if you're trying to expect the top level variable y to be defined inside z appropriately. Again, these are all scoping rules that you've probably encountered already, and we've already probably reviewed. But I'm just briefly mentioning a lot of it a little bit more, just because it is going to come back, especially when you start talking about more functions and deal with more functional patterns like high-order functions. We've already actually talked about our good friend, the anonymous function, the lambda, and the lambda syntax. If you recall, the lambda syntax is nothing more than a backslash followed by the parameters in the head. So the backslash is your lambda, if you will. It's a shorthand for the Greek lambda. You have your list of parameters. It could be one or more, and then you have some sort of value associated with it. Okay. And just as it is, the REPL will actually determine, based on the expression, what potential class constraints can be applied to this. But you could also do what we did before and apply a particular function to that. A particular type signature to that, and we'll go ahead and constrain that anonymous function to this value. All right. One thing to note is there's many other ways of actually defining anonymous functions inside the REPL. This is something that the Haskell book kind of taught me. I didn't realize that this was available. But there's a syntax that we have not encountered in the REPL up until now, just because we've been kind of doing a mixture between the REPL and the file based development that we've been doing so far. All right, and that is, you can define anonymous functions using what's called a block syntax. Okay, so the block syntax, just to show you it without any definitions, is in the REPL. This won't, I don't think necessarily, this will not work if you're writing it in a file. Is encountered by doing colon, open curly brace, followed by a colon, close curly brace. Okay. Now, if we do open curly brace and close curly brace, and then you just do this, sorry, for some reason, locked up, give it a second. I think Haskell just locked up on me. Let me see if I could. I may have to restart Haskell. Your folks watching the stream, you might experience a brief blackout for just a minute while I restart Haskell. My apologies. Okay, and we're back. Let me share my screen here for folks in the actual Hangout. Okay. All right. My apologies, folks. Did not realize that Emacs would block up like that. So let me do this. Let me see this. And we do let trip. So one way, so the block syntax essentially gives you the ability to essentially define the function define the function as is. You can also, use, say, I think blocked up again when I used the block syntax in the normal way. Okay, it looks like I'm going to have to show you guys the block syntax using the terminal because it seems to be locking up when I use it in the Emacs REPL. So let's do that. Let me share a terminal with Haskell running. Give me a second. And then we'll switch back to our example in Emacs, right? Give me a second. Let me do this. Okay. Let me process this up. Emacs. Again, my apologies for this technical delay. I did not expect this to happen when I was playing around with it in Emacs. But this sometimes happens for our demos, so I think you guys are already kind of expecting at some point that this kind of stuff would happen. Alright, so let me share, show you guys in our REPL. Our REPL. The block syntax. Now, this is kind of the notion of the block syntax. You have a colon, the open brace, and you can write any sort of commands, and then at the end you will go ahead and leverage the close colon and the close curly brace in order to actually complete the blocks. All right. The important thing to note there is that when we're talking about the block syntax in terms of anonymous functions, usually what that means is you are probably attempting to maybe name your function. So if you could certainly keep what we had before, x plus 2, okay, colon, integer, arrow, integer. Okay, and we know that this is not right. Hold on a second. You haven't applied. No instance true. Okay. Your arrow integer. Weird. That should have worked. Let me see something here. Arrow x. Okay. X arrow x times 2. And integer, arrow 2. work in this REPL. So what did I do wrong here? Let me see what happens if I do set plus t and we do x arrow x times 2. What happens? Okay, not enough. Okay, I see what's happening. It's you did not apply a function to enough arguments. Okay, so this is kind of expecting me to actually set this up this way. So I'll just show you how to leverage this in the guise of the block syntax. So one way of doing this is, and we've already kind of looked at this, is double could be actually determining integer, arrow, integer, and sorry, because we are using the REPL, we could, write x times 2 here, and colon integer, arrow, integer, and this will actually work. You can see that we've already, we don't need to add this, we can actually do type t double, and we'll get the same signature. Or we could also use the block syntax and say let double and this would be normally what you would write in, say, your file. Okay. You can write let double equals the following syntax, and double equals x arrow x times 2, and you can close it, and it is going to throw, oh, my apologies, I messed up the indentation. I have to keep the indentation all correct. Let double, colon, integer, arrow, integer, and now see how quickly I can do this. Double equals arrow x times 2. And we'll see that we get the same thing. In fact, I think the best way to actually really illustrate this is because since double is already defined, let me recreate this with my double integer, arrow, integer, just to show you that this is also registered correctly. Okay. So now if we do my double, we'll see that it is actually accordingly created to create a function that has an integer syntax. Now, one thing to recognize, and you probably saw this through my some of the errors that we were creating, is specifically when you are at least in the REPL, okay? And Dante on Emacs kind of handles some of this setup for you, which makes it a little bit misleading when you're using the command line REPL. The type signatures, when we specify the type signatures like this, you'll end up, sorry, not like this, where is it? Like this. Because we did not turn on certain things for function showing, what this is attempting to do is it's trying to recognize that there's a function, didn't think that it was being evaluated, and instead of actually just returning the function as is, it ended up just saying, okay, sorry, I can't figure out what show function to use to actually return this. Maybe you haven't applied this function to enough argument, so it's thinking that we're attempting to do a partial function application. So that's obviously not what we were trying to do. We were trying to actually just go ahead and declare the function normally. So if you're trying to declare the function with specific types, the anonymous function with specific types, using the block syntax will help you a lot more than using, let's say, the normal syntax that you're accustomed with. That being said, obviously you could do what I did here, which is here we can actually go ahead and define the function in a single line with the appropriate function signature constraints. Okay. Now you don't necessarily need to provide that. Given that with a lot of anonymous functions, the inferencer can handle a lot of the basic types and accordingly check to make sure that those numerics are all matched. I mean, those type classes are all matched up. So you could just simply pass in, say, an expression and then evaluate it, and it will actually go ahead and call that lambda expression accordingly. But one thing to be aware of is the importance of the parentheses. Okay, in this one-liner here, the expression isn't necessarily created until it can check the open paren and the close paren for the expression that you are the lambda expression that you are attempting to create. So what I mean by that is let's say that we defined our lambda expression like this, and then we provided another value here, thinking that we might have this lambda expression, opened up with no parentheses, and Haskell will somehow figure out a way to actually, recognize the ending of the expression and the beginning of the value. Well, if you're thinking this, think again, because you're going to end up getting this error saying non-type variable argument in the constraint. Because what happened is attempting to take that one and put it as part of the expression that you provided there. All right. So bottom line, you're going to have to put parentheses around your lambda expressions if you're trying to evaluate them on the command line accordingly. Now the exception here is obviously that next thing, but that's a fairly advanced concept. And that is, there's a module in Haskell that allows some version of this called flexible context. However, I haven't actually gone and dug into that particular error and see what might be useful and what might not be useful. One thing to note about expressions, lambda expressions itself, and functions as a whole inside inside Haskell programming and in functional programming in general is, recall, in all functional programming languages, and this is not just including Haskell, one main thing that you need to be aware of is functions are first-class citizens. But what exactly does that mean? Regardless of what language you're writing in, all right, functions being first-class citizens most often means that you could pass them as arguments from functions, return them as results from functions, and so forth. Okay. Essentially, it is treated as any other data type available, any other primitive data type available in the language. Okay, it is itself a primitive data type in that it can determine what inputs and outputs are associated with the function instance, and then it can accordingly take that and constrain it and restrict it at compile time to ensure that functions that are being passed in to other functions match the signature that is being expected by that higher order function. Okay, and we're going to see this when we start talking about higher order functions briefly. But the reason I'm bringing this up is the anonymous function syntax that we've been using this entire time is particularly useful because of its conciseness, especially when you're dealing with passing these kinds of one-liner functions into a higher order function. So you could think of the higher order function as being a template for a sequence of steps. Each sub-step could be customized by passing in that anonymous function or named function, if you want to name it, has an argument into this function for its use in this higher order algorithm that you just created. Okay. You're going to see some common examples of this in a brief minute, but I just want to touch base it here just to mention briefly that lambda expressions, at least the way Haskell has defined them, their real utility will end up becoming very useful when you start dealing with the higher order functions and um, even various forms of basic function applications and so forth. One thing about Haskell that has been particularly useful when defining functions has been their pattern matching feature. We've actually used pattern matching in various shapes or forms in other lessons, especially when we were talking about type classes and we were implementing type classes, because if you recall, when we defined a type class, we actually had to provide all the cases that would fully register that type class for all members of that type. Okay. As a review, you might recall our day of the week example. Let me just do this briefly. Switch us back to Emacs. Okay. And let's get this guy back to Emacs as well. Okay. And let's pull up our PC example. Okay. Obviously, I want this to be there on the right-hand side. Okay. So if you recall our example with day of the week when we were doing something like this example where we registered all the different cases for the EQ type class on rainbow color is an example of us using pattern matching. Okay. And we've seen this even in other cases, like when we were trying to implement other situations of day of the week that used, in rainbow color and day of the week are kind of the same kind of implementation of this. All right. Pattern matching is obviously from this a way of essentially matching values, specific values, against patterns that were defined, and based on those a rule for a particular pattern, if it matches, an action, which is the substitution for that particular rule, will take place, and you'll end up activating that pattern action combination. Okay. Pattern matching allows you to include many different things: undefined variables, list syntax, numeric literals, different data constructors that you provide, and it actually matches against the data constructors, not necessarily the values yet. It allows the ability to create essentially a rules database for small snippets of code that should be activated when a particular pattern is encountered. Okay, this allows you to kind of break up potential logic for a function into these small, concise snippets that, based on again, the pattern that you provide has an input on the left-hand side, as you can see here in our case of dealing with, say, defining the implementation of an EQ for rainbow color. It will look this up and then activate the right-hand side of the function, and it will once the values all match up. Okay. Let's take a actual example with a function, and let's check to see how might this work with normal functions. Okay. Again, we're going to just use integers for our example. Let's create a predicate like let's check it against a constant. Okay. This is an example that I saw in Chapter 7 itself of the Haskell programming language. Sorry, the Haskell book. Chapter 7, page 29. And this is a predicate that just checks to see if a value that was passed in to this function is 2 or not. Okay. So obviously, there's only one case we need to check, and we can do this. We could do this both in the file as we're doing here, or we could do what we did before and use block syntax. But again, since for some reason Dante and Emacs is giving me trouble with block syntax, I'm just going to prefer doing it here. When we're defining a function that uses pattern matching, each rule is a particular function that you need to take care of. Okay, so it's a particular pattern that you need to satisfy. Okay, so in this first case, is it's going to check if it finds 2, and if it does, it returns true. Otherwise, it's going to return false. Now, you've seen this already before, this underscore. What this underscore's name is called the universal pattern. Think of this like your default case inside of a switch statement. Basically, if all else does not match, this will always match. Okay. This is very important because when you're talking about patterns and you have to encounter every single case, but you only have actions to a particular case, you're going to have to actually specify this pattern. Otherwise, you're going to end up throwing that non-exhaustive error that we've seen before. Okay, and I'm just going to show this briefly to you. Let's say that we pass in. We do not pass in this guy. Okay, we just load this up. We see that is2 is provided. Is2 is provided. Is2 is going to actually work if we pass in 2, but if we pass in, say, 1, it's going to say non-exhaustive patterns because we didn't actually provide the actual wildcard pattern, which is the universal pattern that encounters this. Okay. Now, if we actually go ahead and return is it 1, you'll see that it's false. Is it 2, it's true, and so forth. Okay. One thing to realize when you're dealing with these all case matchings, okay? Hold on. So there's a comment. I think also the underscore cannot be used as a bound symbol. Yes, that is. I think you are right. The underscore cannot be used as a bound symbol because of the fact that it is treated as the universal. I think it's because semantically it is recognized as being ignore this. All right, anything that's passed in, just we don't care what it is. It can't be used inside the right-hand side at all, as far as I know. And I think you're right that because of that semantics, it's essentially disallowed on the right-hand side. So going back to what my comment is when you're handling all cases, when you're dealing with pattern matching, especially when you're dealing with this wildcard pattern, one thing that could be overlooked is there might be this expectation that as long as we write the rules and we have all the cases defined, everything will be fine, right? But let's say that we want it to change the order here, right? What do you think will happen if you do this? And in fact, it already tells us this in the file. I didn't think that it would do this, but again, this is one of the beauties of newer versions of the Haskell REPL. What you end up getting is this error. This is actually a warning that says that we have a redundant pattern here, right? The reason for this is we've allowed. So when you load up a function and you're loading up rules and patterns inside Haskell, it is sequentially adding those to the database. So the order in which these are defined really matters. And if you have your generic versions defined before your specific versions, because of the fact that these generic versions, in this case, you have this universal pattern that can take in any input, can potentially will include all the previous ones that are not defined. If you define this and then define a more specific version, you're going to end up getting this overlapping pattern error because it is true. It doesn't do an exclusion once it recognizes the fact that you've defined a different rule for a very specific case. So bottom line, you want to make sure that your order of your specific rules are all appropriately defined before you start talking about your wildcards, your universal cases, and your universal rules. And this includes across the board all the different types that you might end up encountering. All right. So now that we have this, we can go back and actually go and, we get our same errors that we had before. All right. And we already talked about non-exhaustive patterns. One thing to note about the Haskell REPL that allows you to potentially handle your pattern matches and checking to make sure that they're non-exhaustive or not is you can actually explicitly set at the command line, in the REPL, :set w all, which is essentially turning on all warnings. But for some reason, this is locking up again. Okay, so we have this w all now, and if we actually provide, second here. Locking up because I have some stuff that is running. Okay, so let's say that we try this again. Hopefully I don't get this screwed up. Let is it 2 : integer rule. Okay, looks like I'm going to have to switch over to our shell again because I forgot I need to use block syntax for this. Let's go switch back to our REPL. And let me share this here. This. Share. All right. So let's set that up again. Also do this. Sorry, folks, just give me just 1 second. I'll be right with you. Okay. Sorry, there was just some little hiccup here on our connection. Okay, so where was I? Yes. So if we do set WA wall here, we could just go ahead and add additionally this let is it to that takes an integer to bool and is it 2 equals true, and if we go ahead and define it like this, because we turned on all warnings, you're going to end up getting a warning automatically about incomplete patterns saying that the pattern matches are non-exhaustive, and it ends up specifically telling you which functions and which rules can be satisfied and what are not, what is excluded. Okay. This is very useful, especially if you're playing around with it in the REPL, because now you can actually uh, uh, so one of the things is you can now check using, especially when you're dealing with it in the REPL, specific rules that you need to encounter and need to explicitly provide just to test your code as you are interacting with the actual final result. Now, one thing to note, and this is general practice that I've seen in multiple books, it is suggested and often encouraged to actually turn on all warnings because you're told ahead of time, because you'll get this compilation issue. It will, and when I say compilation issue, it doesn't mean that it doesn't compile. Okay, warnings in Haskell work like warnings in any other language. Okay, it will compile, and if you're using :load, it will compile and load inside your REPL. But that doesn't mean you need to. That doesn't mean you should ignore those warnings. Okay, those warnings are there just like warnings are there in any other language. All right. You don't want to ignore a warning, because a warning is basically telling you, while this may work most of the time, there are cases where it's going to definitely never work. All right. And you want to make sure that you encounter those and account for them. All right. An example of this typically in other languages is signed-unsigned conversions that can often happen in compiled languages. All right. You may not necessarily see that here, but it certainly can be the case that if you see a warning like this type mismatch or a generic type to more specific type casting issue, that you may encounter particular cases where it's going to end up giving you unexpected behavior. I wouldn't say necessarily undefined behavior, right? And that is something that is more dangerous. Those are subtle bugs that usually your type checker is actually warning you can happen when you are trying to do something that it's not expecting based on the rules of the type that you provided. Okay. Pattern matching in general gives us the ability to work on different inputs of data and provide different actions based on the inputs that are provided. Okay. And more specifically, pattern matching when it works against data constructors. All right. And when we're talking about data constructors, we're talking about when you defined, if you recall in our example, let me just switch back over here to Emacs to give you guys an understanding of that. Sorry about switching back and forth, folks, but it's just making things a little easier to illustrate some stuff. Okay, and let's go to and folks who are on my call, I especially apologize because Hangouts isn't the best when it comes to switching between multiple windows during the course of a stream. All right. Those on the stream, looks like we are back in business. Just double check in the stream dialog is that we're back in business. Okay, excellent. And for those who are in the Hangouts, please let me know if you can see my Emacs editor. It looks like it's all showing up. If not, just ping me and I'll take care of it. But when we're talking about data constructors, recall, and I'll just pull up our PC example. Our data constructor is normally the ones that are on the right-hand side of a type constructor. Okay, remember when we're defining a type, okay, whether it be data or a new type, we are defining essentially on the left-hand side a type constructor, saying that these are members of this particular type, and on the right-hand side we are providing essentially rules for different data constructors. Okay, now the examples that we've encountered so far, and I'm saying so far, were examples where we're not actually necessarily passing in anything, or if we are, we're passing in something trivial, like in the case of say age, we're passing in just an integer. Okay, but let's say that we are passing in something like say pair. Okay. Pair, if you recall, in this trivial example, it was essentially something that took in a type variable of A, and then it returned essentially a pair of the same, essentially it created, this data constructor basically created a pair where the first and second value are of the same type, all right? So we have, and we've actually used this pair before. If we do 5 and 10, here we see that we get pair 5 and 10. And if we actually do type of pair 5 and 10, we'll see that we'll get pair num A. So that's saying that the type class A is, the type class numeric must be satisfied for A in order for the pair of A to be constructed. The reason why that's important is when it comes to pattern matching, we have the ability to take this data constructor, okay, the right-hand side, okay, and use that to our advantage to unpack and expose specific parts of the data in order to write more specific activation rules for particular functions. What I mean by that is we're able to unpack and grab a particular value, bind it to a particular variable, and then use that for the transformations for a given function that we are defining. Okay, I think here would require a little bit of an example to kind of illustrate when this might be useful for us. Okay. We've already seen this actually when we were talking about unpacking, say, first and second inside of the pair. But I'm going to illustrate this by going through and reviewing the example in the book for dealing with, say, account numbers in a actually, you know what? Let's see if I can actually do this with. Okay, we could do that. Let's just go ahead and do that. We will create. We'll deal with writing a very basic registration system. Okay. So this is in, again, the reference is in the Haskell book. If you guys have it, that we're reviewing, Chapter 7, Section 7.4, page 231. Okay. This is kind of the next kind of example that's kind of useful for us to go through and understand. Suppose you have essentially a type like this, that's username string. Let's say that we have now another type called account number, and our account number is nothing more than a specific integer. And basically, let's say that we have our user, okay, either they are an unregistered user, okay, which means the type constructor, the data constructor takes in no parameters, or they are a registered user, okay, that contain a username and some sort of account number, right? So we now have these things. So now let's say that we are trying to write a function that essentially prints the user information. If you recall again, if we're doing anything with print to the console, all right, we are taking in some user value and we are returning an IO monad. Ignore the monad part, but I'm repeating it just so that folks can understand this type signature, right? For each one of the cases for users, we're going to have to write a rule to determine whether or not we're dealing with an unregistered user or a registered user, okay? User is a sum type, okay? Remember what a sum type is. A sum type is basically a rule of one or more. A sum type is essentially a rule that consists of two or more data constructors, okay? Meaning that either one of these data constructor, when constructed, will become a member of this type, okay? What we can do is we can leverage our pattern matching feature in Haskell to actually determine how might we end up leveraging, how might we end up dealing with unregistered users versus registered users, okay? So in this case, we could just write a rule, for example, for unregistered user by just saying, okay, for an unregistered user, we will go ahead and say put string line, which again is what have you. And we could just put string line is basically a function that returns the IO monad. If you recall, by typing in put string line here, you can see it takes in a string and returns an IO monad. We can also then write, obviously when we did this, we get this warning saying that pattern matches are non-exhaustive. We've seen this already because by default, Emacs with Dante automatically turns on all warnings, so you are essentially dealing with all the different types of warnings that Haskell provides you already. So those of you who are using Emacs with Dante, you are essentially a step ahead in terms of actually dealing with the different types there. So in order for us to satisfy this, we're going to have to finish this off. We're going to have to implement a rule for registered users. Well, registered user requires you to essentially construct a username and account number. So we're going to have to really break this down. So one thing that we could do is, obviously, when we write in registered user, we can say that we have username, okay, because username is a string, okay, so we're binding whatever username is passed in under this variable username, so we could use it within the context of the rule, all right, and we are using account number, and again, this is all related to binding the value with the rule, with the variable name, so we can use it in this function. And what we can do is we can actually say put string line username, so username and we're going to also say account number second here. Okay, let's do this. Okay, and obviously since username is and account number both are of different types, we're going to have to say show here and show here. Let's see what happens. No. There we go. No, hold on. What am I thinking of? Did not match. Okay, so I must have forgotten to. I may have to wrap this around parentheses. Give me a second. Yeah, I'm gonna have to wrap this around parentheses. Actually, no, I don't need to. I could just simply, when you need parentheses, you could always use a $sign because this will actually do the same thing. Okay, because this, let me show you this trick. So first, you could just simply do okay, and this will actually work. Okay, this is actually taking the parentheses, the concatenation, doing the concatenation first, and then taking the result and passing over to put string line. But recall, we've actually encountered this $sign operator for a convenient way to actually get rid of parentheses. So you could just simply, instead of doing this, just run $sign, and you'll end up getting the same error here, same answer. Oh, that is once you provide both the show, because it needs to know that it needs to convert the type into a type string. Okay, you don't need to necessarily do this here, but you definitely need to do it for account number. So now we have actually a function that is actually going to return our account information for a given account that we provide. Okay. So how might we use this? Well, let's see here. Well, we could certainly do this: print user unregistered user. All right, we're good. We got this guy going. This certainly works. But let's say that we want to create a account. Okay, so we could just say let's say sample user equals this. Pull this up a little. User John Doe. Oh well, let's say J Doe, because we're going to try and pretend this is a website of some sort. Data constructor is not in scope. Well, 1 second. Oops, sorry. Wrong thing. Username, sample user. And then sample account is going to be the registered user is actually the user. The username is different. And let's say the account number is, to quote, Spaceballs 1 2 3 4 5. Okay, which is folks don't understand the joke. I encourage you to watch Spaceballs. With these two. These two, the username and account number, we could create a registered user. Let's say that we have that. Registered user, sample user, sample account. So we now have, in our type, we have a user that we could deal with. So now that we have a user we could deal with, we could pass this in, and what happens is in this case, it's going to look up unregistered user, realize that it's not unregistered user, and then sequentially go through every pattern that's been registered until it hits one that occurs. In this case, it will hit the second case, and it will return our account number. All right. So handling all cases in terms of pattern matching, especially when it comes to data constructors, allows you to end up writing these specific rules for a given case, but you must handle all cases in order for the pattern matching mechanism to be to successfully compile all the rules for a given type. Otherwise, you're going to end up getting this warning about incomplete patterns, which is basically telling you if you use this the wrong way, other than the ones that you've already defined, you're going to get non-exhaustive patterns, and you may not encounter this until you hit a situation where you do, right? And that's a very important thing to be aware of. So when you're doing your type design, make sure that when you're writing functions, especially for patterns against data constructors, that you handle all the different members of your data of your type constructor, so that way you don't encounter this issue at all. Unpacking is a very important thing that you should be aware of because you're going to be dealing with it on a day-to-day basis. I encourage you guys to go through some of the examples that are around in terms of handling unpacking, just merely because this is something that you will be dealing with a lot. All right. So one simple example is the use of the wildcard that we saw earlier. When you are encountering a particular, let's say that you are writing a simple consensus application based on location, okay? And this is just for nationality, all right? This is, let's say that we have let's say that we have yeah, let's just do it this way. You have a person, okay, and it's a person that contains name, occupation, name, and place of origin, right? So this is a really dumb application. Obviously, I need to define name as string. Let's do new type. Sorry, name string. Let's say new type place of origin equals, and we're just going to use continents for this. Okay. Let's say let's actually put continent of origin, right? Just to simplify the number of cases. I know that usually it will be country of origin, but obviously there are hundreds of countries, and I really don't want to go through all the examples of hundreds of countries. So let's say continent of origin is continent of origin continent. And then, obviously, we need to define continent. So let's go ahead and define continent as our data constructor here with our 7 continents. Okay, Antarctica, Africa, Asia, Europe, North America, South America, and I forgot one more, A, which is obviously the Arctic. Okay. although technically it should be Antarctica, but you know what, we're not going to go through those. Okay. So, oh, my apologies. I have to create this to be in a data because we can't have data constructors with more than one argument where they're dealing with new types. All right, so let's say now that we are going to be dealing with, say, for example, we want to have different predicates for each type of content, okay? I'm only going to show one example of this, okay? A different predicate for a given continent, okay, is from, let's say, Europe, all right? And this is going to take not a person necessarily, let's say continent of origin, and it returns bool. Now, there are 7 cases, obviously, for writing this rule, and we have to be exhaustive. So we might think one quick way of writing this is just simply pasting this guy, going ahead and writing is from Europe. Okay. And we might end up, obviously taking this guy and deleting this, and then here we might add our case each time for these, and then in this case it's true. All right. So sorry, I didn't mean continent of origin, I meant continent. But the one thing that you need to be aware of is you might have hundreds or even thousands of versions of this, okay? And going through every case is a bit tedious and definitely unmaintainable in the long run. What you really want is, since this predicate is really asking for one specific continent and then everything else can be ignored, what you really want is something that could allow us to, just define that rule and ignore, and everything else should be set to false. So that's easy to write. You could just simply do something like this, and we've seen this already. This is where the wildcard comes in. By writing this, you end up getting a more appropriate issue. All right. Obviously, now that we have this rule, we can now use pattern matching to unpack a particular person to determine what their origin is. For example, we might end up saying, what continent? What continent are they from? Alright, and this is a function that takes in a person and returns the continent of origin. Okay, and obviously what we're going to be doing is the way we write this is we take the person, which takes the name, we don't care with the name, and we take the continent of origin, continent, and what we do is we just return continent. Okay. Did I spell that wrong? Yes, I did. My apologies. Alright, so... Oh, sorry. I have to do continent. Here. Now we have it. Oops. Let me do this here. I forgot to say deriving EQ and show. Okay. Not in scope of a data constructor. Let's see what we could do here. Okay. Actually, I think this is correct. If I do this. Let's see, what did I mess up here? Let me see. Okay. Couldn't match the expression type with the value type. Let's see. Defer type error, constant order with the actual type, continent. Oops. Oh, my apologies. This is because I should be returning the continent here. Now this should all work. Alright, just a error typo on my part. Okay, so we now have our rule here. We're returning a continent based on what we're getting. Okay, and so what you could certainly do is you could use this information to write out other predicates. For example, is Asian. That takes in a person and returns true. And so let me just first, before I write this example, let me first show you that this actually works that we created here. Let's go here and say, let's say Asian person equals, and let's actually name sample name equals Jackie, let's say Chud, alright, and let's say continent of origin is continent sample origin equals CO origin equals continent of origin continent Asia. Okay, so sample CO origin, you can see it is creating continent of origin. And let's say that we get also, let's create our person. Sample person is person, sample name, sample CO origin. Okay. Oh, my apologies. I forgot that this here, sorry. Here should actually be name. Okay. So we now have our sample person. Alright. And let me actually do something here just to make it easy for us to deal with some of this. Let me do this. Deriving EQ and show. Deriving EQ and show. And oops, sorry. Since these are all simple types, we can actually go ahead and the previous types are actually generating this for us. We could also derive this too as well, just so that it makes it easier for us to actually load some stuff up. Okay, so let's see here. Let's see our sample person. Oh, sorry. Looks like I forgot that this restarts. Okay, sample person. We have our sample person here, okay? Now, if we actually ask what continent are they from sample person, you can see that it automatically deconstructs. It deconstructs the actual object, finds content of origin, right? Because again, we provided it the pattern, right? We're ignoring the name. We are ignoring, all this information, and we've essentially said, okay, you know what? Go into specifically continent of origin, find continent, bind it to continent, this variable continent, find the value, and bind it to this variable, and then return it. Okay. Think of this as like an accessor, if you will, right? Of some member variable, but really it's just a simple function, and it can be expanded to any other function too as well. And you can see that this can work on any specific any specific person, okay? But this can also be used to write some predicates, right? Using pattern matching. All right. One is related to, let's say, this example of is Asian person or is from Asia. Okay. And this time we're not taking a continent, okay, like we did with is from Europe. Instead, what we're doing is we are actually writing a specific rule for a given person, okay? So the way we could do this is we could totally first write a rule to figure out what continent that they're from, but we already have that, right? So we can actually take a page from this function and just write simply a pattern that takes in a person, takes in anything, takes in content of origin Asia, and returns true. And then obviously for anything else, we don't need to worry about anything else. We'll just return false. Okay? And this is a satisfactory rule. Okay? And what now, if we pass in our sample person is from Asia to this, let me go ahead and create this sample data here very quickly. Sample person. Okay, sample name. Sample CO origin. Equals continent. And now we could just say sample person equals person, sample name, sample CO origin. Now you don't need to, by the way, you don't need to write this. You could have written all this in the same line. It's just to make things a little bit cleaner. And of course it's going to be complaining about missing type signatures here, so we could just quickly add those two as well, just so that we don't get that. name samples origin document of and sample person equals person. Okay, so this, okay, we have everything loaded. So given our sample person, if we do is from Asia, a sample person, you'll end up getting it's true. And then you can obviously deduce that if we pass in anything else from this, you'll end up getting that it's going to be false otherwise. Are there questions on pattern matching with data constructors? So pattern matching can work not only with data constructors as also with tuples. I encourage you guys to play around with dealing with tuples yourselves, just because tuples follows the same kind of pattern that we've encountered here, which is using wildcards and picking the right location in the tuple to actually determine what is actually being bound, and then using that as part of the lookup to actually go in and finding the activation rule that will actually get executed based on what's being passed in. One final thing about patterns, okay? While it is true that you can use pattern matching for pretty much anything, there might be cases where, say, an if-then-else expression might be useful. So there are places where it's appropriate to use them. So I encourage you to use pattern matching almost as much as you can, but just know that there are cases where it could get potentially convoluted, and you have other ways of writing conditional logic inside Haskell. And this includes if-then-elses, as well as, for simple expressions, it definitely includes this if-then-elses. But it also includes this next thing, which is the last thing that we will, looks like we'll cover, just because I'm surprised that we've already hit our 2-hour case here. But, and that is case expressions. Case expressions are basically if-then-elses, all right, if you think about it. They're kind of like switch statements, but you are leveraging some ways of doing some leverage of patterns as well in cases. The case expression itself, for folks who have seen the case expression, it looks very much similar, and honestly, I can't tell the difference between this version of the expression syntax and where it came from. Looking back at the history, it looks like the case expression that Haskell adopted is very much in line with the ML school, because ML has a lot of ML equivalents, whether it be Haskell, Miranda, SML, or OCaml. They end up having this kind of expression that allows you to write out rules based on what's being passed in for the case expression. The expression itself syntax is of the following, okay? I'm just going to write it briefly here. It's case, the condition that you want, a predicate that you're trying to satisfy, okay? Or it could be of type, if you will, of, and then you can write various rules here as being true or false, okay? There's also in your cases, okay? Now, the cases that we're going to be encountering is really just cases that deal with Boolean flags here, just for examples. Just because the case syntax, again, is basically an if-then-else. right? It's going to check the predicate, and then if it's true or false, it will go ahead and return that. But in some cases, it may also be an enumeration, which will act like a switch statement. Now, this is what makes this slightly different than, say, OCaml. OCaml case syntax actually allows you to write dispatching rules on the inside the case based on the structure that's being passed in. So it's in OCaml, it uses this case syntax to actually do some form of pattern matching too as well. Whereas in Haskell, it's actually built into the pattern matching syntax that we've seen earlier. So let's see an example here. Let's write a sample function, right? It takes an input x, and if x plus 1 equals 1, this is true. Let's go ahead and write sample func takes in numeric a, and then it returns an IO monad. It will actually essentially print something out to the console. All right. So here, in this case, if we do p, we could say put string line you passed in 0, false. It will put string line. Let's just say this, and result equals show x plus 1. Okay, let me do this. $sign. Show x plus 1. Okay. And here we'll say result show x plus 1 equals x plus 1. Great. So, let's do, what is the problem here? Warning, could not deduce EQA rising the use of, oh, sorry. I think I'm going to have to actually put, let me change this to just a string. Okay, and let's just, instead of doing this craziness, let's do x equals 0, or this. Let's do that. X is not equal to 0. And let's see here. Let's see. it is complaining about X, but there isn't anything in here. Let me do this and just see what happens. It should not be complaining. What is the type signature here? Func. Okay. I put only part of this here. I have to explicitly say okay, EQ A. Now we're okay. Cool. We're all good. So one of the advantages of using REPL, right? So now we have essentially a function that takes the case statement. Each of the cases is, just true or false. Nothing's actually being magically handled here. And this here is could now be used inside our sample function. So if we pass in 0, we'll obviously get x equals 0 because the function will hit the true case. If we pass in 1, x is not equal to 0, and we'll just return x is not equal to 0. Each of these is a branch, though. Notice it's basically like an if-else branch to this particular function to handle all the different cases. Okay. Now this can be any sort of function. Okay, and that could take in, for example, if you're trying to write something that checks the palindrome of a function. Okay, as long as you are dealing with EQ, you can actually use the case syntax to write rules like this to make it more explicit as to what your syntax is. Okay, now in terms of let's say checking something, case syntax does not escape you. It does not limit itself to just this syntax. Okay, you could certainly say, for example, why and use a where clause to lexically define the syntax that the predicate that you're defining, have that actually referred to later on. And this might be something that you might end up using for other computations within the context of the actual case. But the result is still the same in that it's going to end up giving you the same, check. It's going to check the thing first against the value condition that you provided, and then it will go from there. It'll actually go in and check to see which false branch or true branch you're actually encountering too. Let's actually try one thing here, which is let's check positive. Let's say we're writing our own my signum, right? This is a thing that will just simply they'll return whether or not you're doing you're using a negative number or positive number or so forth. This is where case really kind of like shines in that it can actually write out each of these, since these are a particular predicate. Specifically the L2, I think the ordering predicate. It'll give us, LT if it's less than 0, or GT if it's greater than 0, and we can return each of these. And if it's an EQ, it's equal to 0, you can just pass in 1. This is a straight up, if you actually look at Signum, this is essentially a straight up definition of Signum in the mathematical literature. So you could just simply write out this rule and get this rule for you. So now we could just see if my Signum takes 0, it returns 0. If we pass in a -1, you'll get a -1 and so forth. Okay. Case does not restrict itself to just Boolean expression. It will restrict itself to anything that will provide some sort of enumeration. Case does not allow you to actually leverage pattern matching syntax, to use pattern matching to dispatch on patterns, okay? If you're going to be writing that, you should write a function, write those patterns built into the pattern matching syntax that's already available that we've just encountered, and then you'd be good to go. You get the equivalence. Case is very, very specific for essentially like a switch, all right? So that is how you should end up leveraging it, at least from what I've read so far. With that, I see that we've gone over. I was going to go and cover higher order functions, guards, function composition, point-free exercises as well. And there's a couple of things in with relation to guards that are also available to you in Learn You a Haskell that I was going to go and leverage. But obviously we are well over our 2 hours. So again, next week we are taking a brief hiatus. The week after we'll cover the remaining pieces of essentially Chapter 7 inside the Haskell programming book. This is chapter, what was this again? It was Chapter 4 inside Learn You a Haskell for folks who are looking at Learn You a Haskell. And actually, it's not only covering Chapter 4. Chapter 7 in the Haskell book essentially is Chapter 4 plus Chapter 6 in Learn You a Haskell. For folks reading Real World Haskell actually has some information on this. I will put down the referred chapters for that as well, just so that you guys can cover some of those bits and pieces of information too. Are there any final questions? Okay. If there aren't any questions, I appreciate you guys all joining me this Sunday. I hope you have a very nice Sunday, and let me know if there's anything I should cover inside the YouTube comments. All right? Thank you, and I'll see you later. Bye.